So in this video, I'd like to discuss, albeit briefly, secondary recovery methods. So secondary recovery methods are defined as processes that are used to increase hydrocarbon recovery from the reservoir beyond primary recovery. Typical secondary recovery methods are considered to be intervention methods implemented during primary recovery to improve projected low hydrocarbon recovery from the primary process. So our focus would be on immiscible water flooding and immiscible gas flooding. Really. So water flooding of hydrocarbon reservoirs is generally an immiscible displacement process, since water is virtually immiscible with hydrocarbons even at high pressures. Gas flooding, on the other hand, gas flooding is actually more of an immiscible displacement process, but it could mirror an immiscible displacement process under certain conditions, of course, depending on the pressure and temperature of the reservoir, the type of injection gas, the composition of the injection gas, and the composition of the reservoir fluid. You also need to take into cognizance the nature of reservoir heterogeneities and types of other extraneous factors. So an attempt to be made to present in descriptive terms secondary recovery, looking at well patterns, reservoir management, and I'll not be discussing prediction methods like stars and Dijkstra Parsons, which are used for calculating recovery under water flood. Many of these analytical methods have been replaced with more robust methods of reservoir simulation. Nonetheless, you will still gain fundamental understanding of immiscible flooding processes using the simpler analytical techniques. So water flooding is the most common secondary recovery method used worldwide to improve oil recovery from reservoirs. The performance of a water flood project in terms of oil recovery depends on many factors, such as wettability, rock and fluid properties, formation heterogeneities, flood patterns, composition of the water, injection rates, production rates. So all these factors need to be into consideration when you want to design the water flood project and install the associated equipment. So even though water drive is used, it's believed that the mechanism is similar, whether you're looking for natural water drive or water flooding. Water drive in microscopic reservoir sections occurs on a scale of flooding as compared to lab scale for core plugs. At this level, there are three factors that govern oil recovery efficiency, which are the mobility ratio, reservoir heterogeneity, and gravity. Precisely how these three factors interact requires careful consideration and can sometimes provide surprising results in enhancing or downgrading oil recovery under the water drive. So correct evaluation of the influence of these three factors amounts to paying rigorous attention to in detail in determining the vertical sweep efficiency across different sand sections. And the vertical sweep implicitly forms an input to simulation models. And one basic thing that the simulation models helps you to do is to solve for your aerial sweep, which is used for successful tracking of aerial fluid movements. So let's look at a few things you need to consider when planning a water flood project. So engineered water drive, that's all water flood is the principal form of secondary recovery practice in the industry. And of course, the obvious reason is that you have water in plentiful supply, especially from the ocean, and which is relatively inexpensive. And then in addition, flooding the reservoir with water is a more stable process than flooding it with gas. So water drive serves two purposes, maintaining the reservoir pressure of the system that is flooded, and then displacing oil towards production wells. In fact, that's basically what the previous lecture on immiscible displacement was all about. So the first bullet point deals with the purpose for engineering a water drive or a water flood project. So the next thing is that fields with high permeabilities, high to moderate permeabilities tend to be preferred for water flood projects. High flow rates have a favorable effect, leading to relative short project duration. So for your water flood, for your displacement process to be favorable, the fields with low oil viscosity tend to be preferred. Of course, so because you want to attain a mobility ratio less than 1. Considering Darcy's law, it can be seen that this condition has the same effect as high permeability. Of course, you know that your flow rate of velocity is directly proportional to permeability and the inverse of viscosity. So the whole idea is that high permeabilities, moderate to high permeabilities and low viscosities would enable you to attain high flow rates. Thus, you can recover more for less time. And of course, that is important considering the time value of money. Perhaps of greater significance, however, is the favorable influence of low viscosity in enhancing the efficiency of oil-water displacement, at least on the microscopic scale. The parametric group which dictates the efficiency is known as the endpoint mobility ratio, and which is given here. This is our mobility ratio. The incorporation of the maximum endpoint relative permeability means that by direct application of Darcy's law, the mobility ratio actually represents the ratio of velocities. The maximum velocity of the displacing phase and to the maximum velocity of the displaced phase. It's quite intuitive to know that, of course, if the maximum velocity of your displacing phase is higher than that of the oil, you would not have a stable displacement. You would have the water racing ahead of your oil. So the significance of having a mobility ratio less than 1 is that on a one-dimensional flooding experiment in a homogeneous core plug, the displacement will be completely stable. That is, the water being injected pushes the oil, since it can't travel faster than the oil, and displaces it in a piston-like manner. And I think I made this point in the previous video. So, of course, this is the more for m less than 1 is the most favorable form of displacement, and means that the total movable volume, which is of course the pore volume times 1 less reducible oil saturation and irreducible water saturation, can be recovered. Water saturation at the producing well can be recovered by the injection of an equivalent volume of water. So it's more like, at least it should be almost a 1-to-1 ratio of injection to production. Conversely, if your M is greater than 1 on account of high viscosity, then your water flood is inefficient or is not efficient. The water can travel faster than the oil, and since it's the water doing the pushing, it does so and channels through the oil. In fact, that's why I put these diagrams. So, and it does so in an unstable fashion. Water breaks through prematurely at the end of the plug, and if M is, for example, if M is equal to 40, it might require circulation of 100 pore volumes of water just to get 1 pore volume of oil. So you see, this is why the mobility ratio is critical, so that you will get, so that your water flood project will be efficient. A further advantage of selecting low viscosity reservoirs is that for a favorable mobility ratio at abandonment, your aerial sweep is quite high. It must be stressed that the piston-like displacement associated with favorable mobility ratio only occurs on microscopic scale. Of course, if you translate it to the field, you wouldn't have that smooth piston-like displacement. You will still have a shock flood front. In the flooding of the microscopic reservoir sections, you must take account of the heterogeneity. You know, you can simulate a homogeneous core plug, but our reservoirs are not homogeneous. And then, of course, you need to take into account gravity as it affects the overall efficiency. So we've considered the purpose of engineering the water drive, which is to maintain reservoir pressure and to displace oil towards the production wells. We've said that moderate to high reservoirs with moderate to high permeabilities are preferred, so that you can attain high flow rates and recover a lot of oil under a short project duration. We have that same effect for low oil viscosity. And then took some time to discuss the place of the mobility ratio, the endpoint mobility ratios, and how that affects the efficiency of your water flood or at a core scale. So other considerations include low volatility, or that's oil which is not so volatile, that's with low gas oil ratios. Because the idea is this, that if the gas oil ratio is low or tolerable, you will not have rapid decline of reservoir pressure due to the gas coming out of the oil. And then one other thing is deep oil accumulations or reservoirs which are significantly overpressured, because the overpressure serves as an additional source of energy. So in now engineering the water flood, you need to consider the production plateau rate. You would recognize that one of the first things you will see in the books is our production profile looking something like this, where this is your rates and this is time. So this is your plateau between the dashed lines. So while this is not a purely technical decision, as economists and management tend to dominate the decision making, the reservoir engineer is involved in making sure that the initial rates do not cause any reservoir damage. And so although this is extremely difficult to prove, and it's difficult to prove, but you could use a number of tools the reservoir engineer could use a number of tools at his disposal to ensure that, because we want to gain revenue from the project, your rates are not too high, just leading to your impairment of your reservoir or your facilities even sanding up. Another thing to be considered is the number of production or injection wells or both. Onshore, there's no great pressure, there's not much pressure when it comes to this decision. Wells can be drilled as desired, but for offshore projects, these decisions need to be made in advance because of your fixed platform and then the slots in the platform that you need to put in. So you don't do this drilling arbitrarily. So where wells should be drilled depends on the initial results of your repeat formation tester surveys, which enable producers injectors to be appropriately located in communicating regions. Because what's the point of drilling an injection well if it will not be able to displace water towards your producer? So communication between the injectors and producers is key. So let me just clear my screen so that it doesn't interfere with my discourse later. Great. So another thing to be considered is your surface production injection facility. So this has been noted to be the most crucial aspect in the design of a water flood project, especially offshore, because it requires for the reservoir engineer to liaise with the facilities guys and the project guys who will install the equipment. What is vital is that the engineer, that's the reservoir engineer, is fully aware of the need to specify capacities for the individual components and ensure they are compatible with one another and with the reservoir being produced. So you need to specify the water injection capacity, separation train capacity, and water disposal capacity. So typically what goes down is that the seawater is injected and pumped usually from a depth. So right there from the ocean is depth, it's pumped to the platform, and then you check for plankton content, that's organic content, to ensure it's as low as possible so it doesn't constitute biodegradation in your well. Biodegradation, yes, in your well. And then also oxygen is removed from the water. That's the function of the aerators, simply because oxygen leads to corrosion. And then the water is filtered to remove solids, which might otherwise plug the formation and reduce injectivity. What constitutes an acceptable minimum size of solid particles depends largely on the nature of the formation and the pore throat size. Standards, of course, will vary from field to field and must be investigated separately. Then the water is injected to the reservoir using a battery of pumps, and of course, it's by the time it comes back to the surface, and of course it goes into the separator for dumping of some of the water, reinjection, and on the production side of the platform, the capacities of interest are those of the separator train and the oily water disposal equipment. So water, oil, and gas are separated in different stages, different pressures and temperatures to optimize the volume of stabilized crude oil. The water leaving the separators still has a fairly high content of dispersed oil, which must be reduced to an environmentally acceptable level, usually 50 parts per million, before dumping the water back into the sea. Earlier equipment to remove the oil from water, it was rather bulky, but these things have been optimized now. So now platforms are equipped with compact and efficient hydrocyclones to achieve the task. This is for removal of water from the stabilized crude oil. So I mentioned the production plateau rate, the determination of the number of production and injector wells, surface production and injection facilities. So let me go on to talk about water flooding patterns. These are quite, I think they are good for historical basis. So water flood patterns are based on the arrangement of injectors and producers in a water flooded reservoir. The patterns are generally designed to improve area superficiency. It's important, however, to note that water flood patterns evolved from conversion of onshore oil fields developed with regular well spacing from primary production to secondary production by water flooding. So the criteria for converting these, typically on all projects, at times when by the time you start having dwindling production from some wells, they are converted to injectors so that you minimize the need to drill new wells, and then of course maximize water injection. And of course it depends on the well density existing in the field. However, pattern flooding is not efficient for developing deep reservoirs due to the high development costs. It is recommended, or it's recommended that reservoir modeling and simulation would guide your water flooding pattern and not just arbitrary water flooding pattern. So we'll just look at some common water flood patterns. So you have the we'll look at a couple of them. Let's start with the direct line drive, and you would see, so what you have, the circles are the producers while the triangles are the injectors. For this pattern, the injectors and producers offset each other directly, and one quick consequence of this direct offset is the fact that you have early water breakthrough at the producers for the direct line pattern drive. So to address this situation, instead of the direct line drive, a staggered line pattern drive can be used. So you see that the injectors do not directly offset the producers. So as shown in figure 5.2, all the alternate rows of injectors and producers are displayed so that the wells do not offset each other directly. In this pattern, the ratio of injector to producers is 1:1, but you see that this comes across like a 5-spot pattern. You see, you have 4 injectors like peripheral to this particular, not super, 4 injectors to this one well, and that's the superiority of the staggered line pattern drive to the direct line drive. The 5-spot pattern is widely used for many applications and model studies. It provides good aerial efficiency. So you see that there's actually some similarities between this and the staggered line pattern drive. So the ratio of injectors to producers is also what. So you see, if you take one producer, you see you have 4 injectors around it, and that's what constitutes the 5 spots. I think that should be 4:1. And this is a 9-spot pattern. This is widely used for low permeability reservoirs. Here you see for 9-spot you have 8 injectors to 1 producer, at least per pattern, and that's the whole idea. This is a case where it's inverted. You're actually having 1 injector to 8 producers, So this is an inverted 9-spot pattern. This is peripheral flooding, and it was developed when injectors were located around the boundary. So this kind of um, mimics edge water drive. This mimics edge water drive that you see, because you have the injectors surrounding the reservoir. So if the injectors are located along one side of the reservoir, it's a line flood. Peripheral flooding is generally used in reservoirs where the objective is to maintain reservoir pressure, minimize water production, and improve oil recovery. And this will even be good if your production wells are crestal in the center, so it can provide good aerial sweep. So you have other patterns, that's the regular four spot pattern, this is the skewed four spot pattern, this is a three spot pattern, this is a two spot pattern, this is a seven spot pattern. So it's not necessary to replicate these other patterns here, since the engineer can devise flood patterns best suited to the zone development using modern reservoir simulation tools. So when it comes to design of the water flood, you will see that this follows a process, reservoir modeling and simulation process. I wouldn't run through everything, but you see, construct the geologic model, analyze fluid properties, construct the model, run prediction cases, optimize the water flow design. So all this is done using the simulator prior to pilot projects, so that you can look at different water flooding patterns, even those that are irregular, and see whichever one optimizes your injection and production rates. And then you also look at the economics, can produce. It's after you've done all that, done sensitivity studies, that you go ahead to conduct pilot projects. So when it comes to the case of management of the water flood projects, you need to consider, of course, and you see this, what I'm highlighting kind of mirrors a little when we talked about planning for it, but it's good for emphasis. So one of the important things to aspects of the project to be properly managed is the injection wells. So one of the key measures of a successful water flood project is achieving and maintaining the desired levels of your water injection rate. So you want your injectivity to stay good. Water injection wells may exhibit reduced injectivity over time due to the building up of scale and plugging of formations from solid deposits. It's important to test the injection wells periodically, and one key test that can be carried out is the fall-off test, and that reminds you that we mentioned this under our well testing class. The condition of an injection well may be monitored periodically by preparing a hole plot on the performance of the injection. So the hole plot can be prepared from data routinely collected in the course of monitoring the well. These data include cumulative water injection and injection pressure versus time. In this course, you wouldn't be required to plot to make the whole plot, but it's still good for you to know what it's all about. So the method is based on the radial form of the Darcy's equation, where instead of oil, most of these parameters are replaced with that of water. This is actually the Hall's plot. So you see on the x-axis is your cumulative water injection. Here is the product of the difference between the injection pressure and the average pressure and time. So what this goes on to indicate is that for A, you're having good injectivity. So you see, for C continues the trend in A. This means that you have no change in the permeability at your injector. However, if after plotting the whole plot and then the trend follows B, it means that you have significant flooding. If you're having D, you are actually creating fractures in the reservoir, whilst CE is indicative of stimulation. So probably you had to do some remedial work on the injector well to be good to produce the whole plot both before and after the job. We've talked about the monitoring the injection well. So the next thing will be the injection water. So you must have injection water of considerable in sufficient quantities, whether it's from the ocean. And as the project matures, this water will be recycled and used to make up volumes of the injection water. So you will need to test for the quality of your injection water by doing a complete water analysis, because you must show that your source of water is compatible with the formation resistivity water and the formation, so that it won't lead to swelling of clays around. This would impair your injector well performance. The injection water, if not treated, can cause corrosion. And that takes us back to where we're discussing the surface injection and production facilities. Could lead to corrosions, solid precipitation, and even growth of bacteria. So, and that's why you need to check the plankton levels before water is injected. The major cause of corrosion is dissolved gases, and that's why the water needs to be deaerated before it's pumped in. So you will also monitor your production wells. So they need to be tested frequently. There are several. You could use different. The build-up test comes to mind in determining whether there is damage and what the extent of the damage is. You could also run profile logs. These are basically production logs to check flow profiles, and also to determine whether there's communication between you. And of course, you could also do an injection test, of course, to check communication between your injectors and producers. You also need to take regular samples of your produced water, basically to check the environmental impact of your project, and to ensure that what you are disposing is not harmful to the environment. And of course, you need to look at constantly, you need to do frequent inspection or routine inspection of your facilities to be sure that your facilities are not corroding, and to ensure integrity of your facility. So corrosion engineers should routinely monitor facilities with the project for corrosion, and also put in preventive measures to forestall corrosion of the facilities. So let's look at gas flooding briefly before we end the class or this video. So gas flooding is presented in this chapter as an immiscible displacement process. And of course, immiscible displacement occurs in displacement processes where there's a distinct interface between the displaced fluid and the displacing fluid. This includes displacement processes that are near miscible. So key factors that determine whether the gas flow process is immiscible or miscible are reservoir pressure, reservoir temperature, composition of the injection gas, composition of the reservoir fluid, and then reservoir heterogeneity, such as faults and permeability barriers. The impact of each factor can be determined in lab using lab experiments, and then also modeling the displacement process. And interestingly, in what should be my last video, there will be some mention of the role of visibility. And of course, that will be when we're discussing enhanced oil recovery processes. So gas flooding is sometimes used instead of water flooding because at the microscopic level, gas flooding is actually more efficient than water flooding. Of course, in some cases. Plus, some of the injection gas can dissolve in the reservoir fluid to reduce the reservoir fluids viscosity and density, thus improving mobility. This is covertly talking about miscibility to some extent. On the other hand, the volumetric sweep, volumetric sweep is composed of both aerial and vertical sweep efficiencies of the gas process is generally low due to gravity override and viscous fingering caused by high mobility ratios of gas in comparison to liquid. So when in view of the mobility ratio, the gas flooding is a very unstable process. And this is viscous fingering. So you see, what you actually desire is for your gas to be behind the oil so that it sweeps your gas towards the oil. But what you're having fingers of your gas into, so these fingers are not carrying out any displacement. And here you see, due to the gravity effects, you're having your gas going over the oil, and what you actually wanted it for was to have that piston effect. So this is gravity override, while this is viscous fingering. And this effect can be compounded in low permeability reservoirs or reservoirs with severe heterogeneity, such as reservoirs with faulting and permeability barriers. So mobility ratios of gas displacement processes can be reduced by implementing a water alternating gas displacement process, which is WAG, water alternating gas. So the volumetric sweep can be improved by application of WAG. So if you look at the schematic, and I got this off the internet, I don't have copyrights to these images. So you see, there's alternating water, CO2. So the whole idea is to ensure that you're having a good sweep as compared to if it was just the gas being flooding the reservoir alone. And you see, I know we're supposed to be discussing immiscible displacement, but immiscibility comes in. And that's why it's difficult to discuss gas flooding as a pure immiscible process. So let's look at applications of gas flooding. So primary applications of gas injection into the hydrocarbon reservoir are so applications of gas injection for pressure maintenance, gas cycling, and fluid displacement. In many gas injection projects, there are three primary functions. These three primary functions are achieved at the same time to some degree. Pressure maintenance by gas injection is routinely implemented in many reservoirs. Reservoirs that are good candidates for pressure maintenance may have experienced steep reservoir pressure decline during primary depletion, or even which would have been accompanied with development of the secondary gas cap or enlargement of the primary gas cap. For such reservoirs, gas is injected into the gas cap at sufficient volumes to reduce or stop the decline of the reservoir pressure. In some cases, gas injection for pressure maintenance is initiated close to the start of the project so that to prevent decline of reservoir pressure. This practice is used in some cases to keep reservoir pressure from falling below the bubble point for oil reservoirs or dew point for gas reservoirs. Gas cycling is used to improve recovery from condensate reservoirs. I think you should take note of that. So gas cycling is used to improve recovery from gas condensate reservoirs by vaporizing fluids that may have condensed in the reservoir with the jet. We must have dealt with the concept of condensate, retrograde condensation rather. So gas cycling helps to stop that process so that you are having um, fluids that have condensed from your gases being vaporized and therefore being produced at the surface. Gas cycling can be used also to improve recovery from secondary gas capture. Now, in many steep dipping reservoirs, gas is injected at the crest so that you can also leverage on gravity drainage, and typically that gives you a gravity stable process. Gas falling in horizontal reservoirs can lead to gas gravity overriding, and we've seen that earlier, where injected gases rises to the top uh, because it's less dense than oil. Severe cases of gas gravity override rather can lead to low volumetric super efficiencies, leaving large portions of the reservoir unswept. And we've talked about the use of water alternating gas as a strategy to stem this, to improve your volumetric sweep. So looking at gas flood design, the first key factor to consider is obtaining a fluid property model that describes the interactions that occur between the reservoir fluids and the injected gas. These interactions can be both physical and chemical in nature. For instance, lean hydrocarbon gas is capable of physically vaporizing light hydrocarbons from reservoir oil. Carbon dioxide can dissolve chemically in reservoir oil to reduce density and viscosity and improve its ability to flow. I know that we ought to be discussing immiscible gas flooding, but it's difficult to talk about gas flooding without uh, referring to some degree of miscibility. So a key thing is to fit an equation of state to your processes, to your recovery process as modeled using PVT studies or slim trim test or core flood experiments. And then this can now be uh, an input into your simulator model. The second factor to consider is a proper geologic and characterization, proper geological modeling and reservoir characterization. And I won't go into that because that has been. So in managing gas floods, you also need to monitor your gas injectors, simply because injectivity may decline with time due to plugging of perforations from wax, asphaltene, hydrates, and of course, you might need to carry out some remedial actions to um, get back your injectivity. If the profile injection logs indicate unfavorable uh, distribution of injector gas across the interval, then some remedial work will need to be done. If injected gas is carbon dioxide or flue gas, the injector should be completed with equipment that resists corrosion. And of course, you need to still inspect from time to time. Also, you need to check producers, and in fact, you need to monitor your gas producers for gas overrides, for channeling, and there are some analytical techniques and, of course, numerical tool for doing this. If injected gas is allowed to flow to producers without contacting unswept portions, then the volumetric superefficiency will be quite low. And then, of course, you have gas overrides and channeling. This problem can be remedied at producers by isolating intervals showing high gas production with packers or squeezing them with cement. Basically, you're just screening out problematic zones which are producing your injected gas preferentially to, as opposed to your oil or your desired reservoir fluid. In most gas floods containing carbon dioxide and other corrosive injectants, you need to have corrosion resistant equipment. You also need to look at your processing facilities, uh, which include gas injection facilities, separators, stock tank, flow lines, gas plants. These facilities must be fitted with must be corrosion resistant, and of course, corrosion resistant just means that it minimizes, doesn't give way at corrosion easily, and of course, you need to inspect regularly so that you can check the initiation of corrosion. Reservoirs under gas flood require extensive program of monitoring and surveillance. The program depends on the type of gas flood product. Progression of gas flood products are quite rapid due to high gas mobility. Therefore, it's recommended that the gas flood product must be managed with a reservoir model.